Okay, today we are going to look at chapter section 7.3, solving exponential equations. Before we're able to do this, I wanted to take a bit of time to review some laws of exponents. So, if I can find full screen here. So in the warm-up here it says summarize the exponent laws below. So we're going to take a look at some of these and just get a refresher on how these work. Now, same base, x to the a times x to the b. It's important that they have the same base here because then we can simplify it to a single base and just call this x. And this would be x to the a plus b. So be careful, even though we're multiplying the bases, we're actually only adding the exponents. And I'll show you why. If we used something like 2, let's use 2 to the 2 times 2 to the 3. Now, if we were to multiply this all out, 2 to the 2 would be 2 times 2. 2 to the 3 would be 2 times 2 times 2. And if we multiplied these all together, you notice that we only have 5 here, 2 to the power of 5, not 2 to the power of 6. So we're adding the exponents. All right, moving on. The next law here, x to the a divided by x to the b. Again, very important that we have the same base. They're both x. And in this case, it's the exact opposite of what we just did over here. This would be x to the a minus b. Similar to what I did before, if you wanted to use something, let's say 2 to the 5 divided by 2 to the 2, you could do the exact same thing by expanding these out and proving that this happens to be the case rather than dividing these two things. X to the a all to the power of b. Now here is where we actually do multiply our exponents. This is x to the a times b. And again, you could prove this similarly or verify it similarly by using sort of a common number here. If we did 2 squared all to the power of 3, if we wrote this out, well, that would be 2 times 2. Now if we raised 2 times 2 to the power of 3, it would be like multiplying 2 times 2 by itself 3 times. So there's 2 times 2 to the power of 2, and here's 2 times 2 to the power of 3, and you'll notice that it's basically 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the power of 6, which is 2 times 3 for those two exponents. Okay, so that's those ones. Let's keep moving on here. Try to make a shorter video today. X to the power of 0, anything in the whole world to the power of 0 is 1. That's it. That's the whole law. Power of 0 gets 1. X to the minus a. Now, when you have a negative exponent, it's the same as a positive exponent, but in the denominator. So 2 to the minus 2 can be rewritten as 1 over 2 to the 2. So just flip it to the bottom, make this positive. F, x to the x over y, both to the power of a. These can be treated as separate and both raised to the same power. Since they're in the brackets, that power gets applied to both the x and the y. Alright, moving on. X over y to the negative a. Now, you could write this as x to the minus a over y to the minus a, but I don't like these negatives. So when we have a negative in an exponent, we flip it to the opposite side. So we can put the x to the a in the denominator, and the y has a negative as well. So if we flip it, then it can get a positive exponent as well. So we end up inverting these two, and just giving them positive exponent. xy to the power of a, this simply, the a gets applied to both of the variables within the brackets, and we get x to the a times y to the a. I is x to the 1 over n. Now this one's interesting. I don't know if you've had experience with this one before, but n becomes the radical index, and the numerator becomes the exponent within the radical index. X to the numerator taken to the nth root. So for example, x to the 2/3 would be the same as the cubed root of x squared. And cubed, yes, sorry, that was a bad 3. There's a better 3. Okay. So x to the numerator taken to the denominator root. Finally, this last one here, second last one, I guess. J, x to the m divided by n. Now again, this is kind of what I just showed you there. This is the nth root of x to the m. I hope we won't encounter too many of these. Okay, if b to the m is equal to b to the n, so they have the same base. Now in order for these things to be equal, they obviously have to be raised to the exact same exponent. For example, if this was a 1 and this was a 2, then there's no way that these two things could be equal. So they have to be equal to each other, so m must be equal to n. This is going to be one of the most important properties that we use in this section when we are solving exponential equations. Alright, write each of the following expressions as a power of 5. So this is basically an operation where we manipulate the base and we just kind of write it. It's not really a change of base, it's more like just a manipulation of the base. Okay, but let's see how this is done. 125 can be written as 5 to the power of 3. So we just want to try to write everything, all of these, as 5 to the power of something. Now, this one, 1 over 25, this would be 1 over 5 squared. But we don't want 1 over 5 to the power of something. We want 5 to the power of something. So we can flip this up to the top instead and change the sign on the exponent. 5 to the power of minus 2. 1. Anything to the power of 0 is 1. So if we want our base to be 5, we raise it to the power of 0 and it will give us the answer 1 that we desire. 25 to the 10. Here is an interesting one. 25 can easily be written as 5 squared. Now, we use one of the other properties we looked at on the last page. 5 squared, all to the power of 10, and this can be simplified as 5 to the 20, where you multiply your two exponents together. 625 to the power of 5 quarters. Gross. First, let's deal with 625. 625 can be written as 5 to the 4. You can verify that with your calculator if you want to. And now we are going to raise this thing to the power of 5 quarters. Now, when we raise an exponent, take the power of a power, again, we multiply the exponents. So we go 5 to the 4 times 5 quarters. Now you notice when you multiply that, the 4's cancel, and we simply end up with 5 to the power of 5. And we're done with that one. The cubed root of 25. So the cubed root, let's write this as 5 squared. Now, we know 5 squared, if we go back and look at our law back here, this is the one in question. So x to the m taken to the nth root can be written as a ratio, x to the power of m divided by n. So m, numerator, n will be the denominator. So 2, numerator, 3 will be the denominator, and we can simply write this as 5 to the 2 thirds. And that's that for that one. Alright, moving on. Here's the focus on. I'm going to breeze past it. I'll leave it to you to read through it if you want to. Exponential equations. An exponential equation is an equation that has a variable in the exponent. Exponential expressions can be written in different ways. It is often useful to write an exponential expression using a different base than the one that is given. This information you can also find on page 359. Okay, so that's all I wanted to say about that. These ones rewrite each expression as a power with a base of 3. So we want a base of 3. 27 can be easily written as a base of 3. We know that 27 is 3 cubed. 9 squared. Interesting. So we're going to leave this squared aside for now, and let's just rewrite 9 as 3 squared. Now that's 9. So we've taken this and we've replaced our 9 with that. But the 9 was also squared, so this has to stay right there. 3 squared, all squared, would give us 3 to the power of 4. And you find out if you did 9 squared, you know that 9 times 9 is 81. And if you did 3 to the power of 4 on a calculator, oh, there it is. 3 times 3 times 3 times 3 equals 81. Same thing. 3 cubed versus 9 squared. They are exactly the same. Here's a nasty looking one. 27 to the 1/3 times 81, the cubed root of 81, all squared. Let's deal with one thing at a time. 27 to the 1/3. Now, 27 to the 1 will be the radicand, which is just 27. And the denominator here will be the radical index, which is 3. Now, what times itself 3 times will give us 27? The cubed root of 27 is 3. So this whole circled thing just simplifies to 3. Now let's try to deal with this. Nice circling job, doll. Just obscure every number that's important here. Cubed root of 81, all squared. Now, what can we do with this thing? This is nasty. When we square something that's the cubed root, we can't make these things cancel. If we wanted to cancel the cubed root, we would have to cube this whole thing. We can't do that. So we have to leave this for now as a cubed root. And we're going to leave this squared out here as well. But let's rewrite this thing in here. Because 81, we know, can be written as 3 to the power of 4. We did it right over here. Okay, now we can start dealing with this thing. 3 to the numerator taken to the root of the denominator if we wanted to change this thing into a fraction. So we rewrite this part as 3 to the 4/3. Now this whole thing is still going to be raised to the power of 2. So we're not done yet. 3 times, now 4/3 multiplied by 2. Just do it big over here. It looks like this. And we would end up with 8 numerator, 3 denominator. So this is 3 to the 8/3. This is essentially 3 to the 1. Now 1 with a denominator of 3, we're just finding a common denominator. This one can be written as 3 to the 3/3. times 3 to the 8 thirds. Now the reason we get a common denominator is that we're going to have to add these exponents. When we multiply powers with like bases, we add the exponents, if you recall from page 1. So this ends up being 3, and 3 plus 8 is 11, and your denominator is 3. And there's our answer. Okay? So, the your turn on your handout, I would like you to give this a try on your own. So in a few seconds, I'm just going to ask you to hit pause. And if you don't hit pause, then you're going to see the answers right away and lose your opportunity to try to do this on your own. But I guess that's your choice. So if you want to try these 3 on your own, hit pause now. So you probably didn't hit pause, so I would say welcome back, but I'm just going to bring out the answers for you anyway. I haven't shown you the solutions, so this still won't ruin it if you wanted to go back and try to work towards these solutions. There you go, or these answers. There you go. Example 2, solve each equation. This is where we actually get into the meat and potatoes of this section. 4 to the x plus 2 equals 64 to the x. Now, how on earth do we go about solving this thing? It looks like complete Greek. But this is why we got so much practice changing our base. We know that we can write 64 as base 4. So right now we have 4 to the x plus 2 equals something. 64 happens to be 4 cubed. 4 times 4 is 16, times 4 again will give you 64. So we can write 64 as 4 cubed. And this whole thing is brought to the power of x. Now again, when we take the power of a power, multiply the exponents. 4 to the 3x. So 4 to the x plus 2 equals 4 to the 3x. Now, in order for this to be true, since they have the exact same base, x plus 2 must be equal to 3x. Because if these exponents are different, then they're going to have very different values. And we know that's not true because it's an equivalency. So in order for this statement to be true, x plus 2 must equal 3x. So let's subtract an x here, subtract an x here, and we end up with 2 equals 2x. Divide both sides by 2, and we get x equals 1. Now we can go back and verify if this is true. 64 to the 1 would be 64. 4 to the x plus 2 would be 4 to the 1 plus 2, which would be 4 to the 3. And we know that 4 cubed is 64, so we get 64 equals 64 if we go back and plug 1 in for each of those. Alright, on to the next one here. Let's see what kind of magic we can work with this one. 4 to the 2x equals 8 to the 2x minus 3. So this whole thing, 2x minus 3, is a power. Now, it indicated here to us that we're purple, that was an accident. That we're changing the base to solve these. So again, you're going to notice that 8 we cannot write with a base of 4, because 4 to the 1 is 4, and 4 to the 2 is 16, so we completely leapfrog 8. But we can write 4 and 8 with a base of 2. So let's give it a try. 4 can be written as 2 squared. Now this whole thing is brought to the power of 2x. 8 can be written as 2 cubed. And this whole thing is brought to the power of 2x minus 3. So again, the power of a power, 2 times 2x would be 2 to the 4x. Power of a power, we multiply 3 into this whole thing. So 3 goes into 2x minus 3. And we end up with 6x minus 9. So 2 to the power of 6x minus 9. Now again, they have the same base. So in order for these things to be equal to each other, their exponents must be identical, meaning 4x must be equal to 6x minus 9. And pen stopped working. Here we go. So let's subtract this 6x over, I guess. We get minus 2x equals negative 9, and x equals positive 9 halves. Okay, so that's that. And meaningless page. Let's see what's going on here. Oh, just making dots on it. Useful. Oh, that shows the check. Okay, don't care about those 3 dots. Alright, so that just verifies our answer. X equals 9 halves. Here's the check. This is what it would look like. 4 to the 2x, where x is 9 halves. The 2's will cancel. This is 4 to the 9, which is a massive number. And again over here, 8 to the 2x minus 3. So this would be 8 to the 9 minus 3, which is 8 to the 6. And it would give us the exact same thing. Left side equals right side. And we're done. Okay. Here's your turn, the second your turn on your handout. Again, you can go ahead and try this on your own. So spend a few minutes trying to solve this, and when you come back, the answer will be displayed on the screen for you. So hit pause now. Welcome back. Here are the answers. The graphs are included here. So x equals 3 and x equals negative 3/5 for the second one. And this is what the graphs look like for you. So if you had technology available at home, or I guess if you're on the computer watching this, so you have Desmos at your disposal. Finally, whoa, back off. Okay. Solving problems involving exponential equations with different bases. Let's see if we can work our way through this one here. Christina plans to buy a car. She has saved $5,000. Wow, good for Christina. The car she wants costs $5,900. How long will Christina have to invest her money in a term deposit that pays 6.12% per year, compounded quarterly, before she has enough to buy the car? So she needs $900 more here, and she is making she's making 6.12% compounded quarterly. So this is the formula for compound interest. A future value is P, the principal, times 1 plus I to the power of n. You know that from your foundations class. So let's see if we can make this thing work for us. We changed I, because it was compounded quarterly, we changed it to the amount of interest you will earn every quarter. Okay, so that's this number right here, 0.0153. All right, which is 1.53% per quarter, which would give you 6.12 per year. Now, we have everything we need to work on this equation. 5,900 equals, that's the future value. Now, principal is 5,000, and this is 1 plus 0.0153 to the power of n. Now, n is the number of compounding periods. This is actually what we want to solve for. So let's go ahead and divide both sides by 5,000 and get rid of this term right here. So divide by 5,000. Okay, so we substitute the known values in, and when we divide by 5,000 we get 1.18, and this 1.0153 to the n is just this plus this. It just lumped them together into one, and to the power of n. So let's see what this looks like. Oh. That ain't great. Okay, here we go. Okay. So, we can use a graphing calculator for this one. Enter the single function y equals this one. And now we've subtracted our 1.18 to the other side, just so that we can enter this as a single equation and identify where the graph intersects the x-axis. So let us go into our Desmos. Sorry I didn't have this queued up, but I'll edit it out. Okay, so we have our equation ready here and our line graph, and you can see the x-intercept here, 10.9 and 0. So the x value that solves this equation for us is 10.9. So when x equals 10.9, we can take that back to our problem. $10.9 represents the number of compounding periods. Now it compounds 4 times a year. So we have 10.9 in our solution here. Compounds 4 times a year. So 12 compounding periods would be 3 full years. So this will be just under that. And you can see here that because it's compounding quarterly, it will take 11 compounding periods, which is just a rounding of 10.9, which is 2.75 years. So it's just 1 compounding period shy of the full 3 years.